Welcome back to CE 528. And now what we are doing is we are picking up our discussion from the first lecture class that we had. And we had the discussion about desirable properties of the measures of effectiveness. And now we're talking about system constraints. So system constraints can be physical, economic, financial, political, and environmental. And sometimes if you use some hard targets or self-imposed hard targets, they're also a particular type of constraint. So there are typically constraints related to system resources, which may be either inside or outside the system, depending upon the degree of control that is exercised by the system managers. So again, if the system managers have a lot of control, then you have those constraints can potentially be relaxed. But if it's a more of a system outside the system constraint, then it acts more as a constraint rather than as an input. So we just have to be careful about when we're thinking about these things is that how much control do our managers have? And that'll determine whether it's an environmental constraint or a real constraint that's outside the control, or is it something that our managers can control? So it's sort of a system characteristic. So we talked about this. Oh, I think we talked about this as well, right? So we talked about how systems could be open and closed. Oh, I'm thinking I already talked about this. So let me. My apologies, folks. I think we talked about this as well. Okay. No, I think we talked about this as well. Can now somebody remind? Okay, principles of evaluation. Thank you, Bella. So principles of evaluation. Yeah, that's kind of what I was thinking now. We did this. Is this where we were? Principles of evaluation. No, yeah. Yeah, no, we did that. Yes. Okay, yes, this is where we were. Now, when we were talking about, so my apologies for some repetition there, but we were talking about principles of evaluation, and that's where we stopped. I should have made a note. Of that. So decisions should be based on future outcomes. The past history is irrelevant, and we talked about how we shouldn't get into this sunk cost fallacy, and then we have to look at the issue on impact on different interest groups, and then impact should be measurable on the same dimension. And then the other set of principles that I want to start talking about today is that the dollar impact should be expressed in constant dollars. So typically what we'll do is we'll have everything impacted in 2020 dollars or 2018 dollars. So we're accounting for inflation. Now, when we do typical accounting processes here, we don't really account for inflation necessarily. Why we don't do that is that because the idea is that as long as we are accounting for the nominal dollars, because inflation is going to affect all different alternatives in the same way, and that's why we don't have to worry about it. So if you want to do constant dollars, so then you basically do current dollar amount or nominal dollar amounts, and then you subtract inflation from it. So basically adjust for the reduced buying power of the dollars. But typically we don't have to worry about this because we don't have to worry about inflation in benefit cost analysis because we assume that all of the alternatives that we are evaluating are going to be similarly impacted. Now there is one exception to that, and we're not going to actually worry about that exception in any of the problems that we are going to do or any of the labs that we are going to work on, because that's not going to be relevant there. But I want you to be aware of that there might be alternatives that maybe use a particular resource that it's going to be impacted by inflation more than others. So here is that example here. So let's think about a project where you are looking at alternatives that may be more dependent upon gasoline, right? More dependent on gas. And we know that the gas prices are going to inflate higher than the nominal inflation, normal inflation index. So think about this. This is showing you data for 4 years, 1, 2, 3, 4 on the x-axis. You could see that. And let me go ahead and annotate that with spotlighting. So you can see that there are year 1, year 2, year 3, year 4. And then you could see that if the inflation index is 5%, then the factor that you're going to use to determine the buying power of the dollars, it's going to go up by a factor of 5%. So it's 1.05, and then it's 1.05 squared, and then it's 1.05 cubed as we move on to different years, right? But if you think about the gas prices, if you anticipate that the gas prices are going to rise, by 20% rather than 5%, and everything else is going to increase in price by 5%, but we know that the price per gallon of gas is going to go up by 20%, then your price per gallon used would be, price per gallon of gas would be 1, 1.2, and then 1.2 squared, and 1.2 cubed. So the price per gallon that you're going to use in your evaluation, it's going to be how much higher relatively is the price compared to the normal price increase. So then here 1, and then this second, the price per gallon used in the calculation will be 1.2 divided by 1.05. Because what you're doing is you're trying to figure out how much additional price increase would there be when you use gasoline. So that's the price we need to use. And that will come in useful when there is one alternative that is relying on that more expensive or rapidly inflating resource. Okay, and then you could see the same thing for the year 3. It's 1.4. So it's basically just the division of this row by this row. So 1.44 divided by 1.103, and then 1.728 divided by 1.157. And then you could get that relative gas inflation index is just 1 plus y over 1 plus x minus 1. So it's just a matter of z. You could figure that out easily. So 1.143, 1.306, 1.493. You can make those estimations rather easily. Okay, but again, we're not going to work out any problems that require this type of calculation in the exams or in the tests, but this is something that you have to be aware of. Now, we don't typically use this type of calculation because these things are actually very hard to assess beforehand. You know, it's hard to tell how gas prices are going to be relative to the overall inflation. It's hard to say that, and that's why we typically don't get into this calculation. You might run into a situation where you might have to do this kind of calculation. Maybe you're applying for a grant funding and the agency requires it or something like that, right? So there could be, maybe there is a project where you're gonna maybe progressively acquire more land, and then the land prices are rising faster than the overall inflation, things like that. So there could be somewhere where this could be relevant. So it's good to know that these types of calculations is something that could be done. But again, we're not going to use it in the class. So when you are doing this evaluation, the differences between alternatives are really relevant. Everything else, you know, our goal is to highlight differences between alternatives. As much as possible, separable decisions should be evaluated separately. So for example, if you're looking at evaluating metro lines, we typically don't try to compare alternatives between one line of the metro to the other line of the metros. So typically evaluation principles will be more applicable when you are trying to assess different alignments of the same metro line that's roughly serving the same population and stuff like that. One measure of performance should reflect dollar quantifiable impacts. Non-dollar quantifiable impact should be incorporated using appropriate methods, and we're going to talk about some of those. So again, so one measure of performance could be, so what do you think are some, so my question to you is, what are some of the measures of performance that reflect dollar quantifiable impacts? Can you think of some example measures of performance that reflect dollar quantifiable impacts? Any thoughts? You can type that up in the chat. Give you maybe 30 seconds to do that. So let me, so yes, so some of you mentioned the fares and maybe reduced cost because you saved some crashes and collisions. So reduced cost because of that. So yeah, those are all great measures of performance. And then typically we'll combine them into net present worth or benefit cost ratio and whatnot into one measure when we do evaluation. And then we have to think about what does our non-dollar quantifiables measures might look like, and then we incorporate that. We'll learn to do that too. So one way of doing that is to think about the trade-off cost or the net present worth with one non-dollar quantifiable measures of performance. So for example, although it can be done, but let's say you don't want to quantify the number of lives that you save because of some safety improvement that you're making on the road, although that can be done because Caltrans and Federal Highway have, like, you know, a cost associated with each fatal crash versus each injury crash. But let's say you want to account for lives saved per year as a non-dollar quantifiable measure of performance. And then on the other side, you have the cost of each alternative. So these little ugly stars that you see, or these bubbles that you see, these 4 of them. So these are basically your alternative A, B, C, and D, right? So you could think of these as, so I'm going to just draw it freehand. So let's say this is alternative A. I want a different color now. So maybe this is B. Let's say this is alternative C and this is alternative D. So these dots represent the 4 alternatives. And I'm plotting how much on the X and Y axis. Maybe I'm plotting the dollar amount here on the X axis, and then the number of lives saved here on the Y axis. And I just plot for each alternative, I just plot the point. So this is the cost here. This is the number of lives saved. This is the cost for this alternative. Number of lives saved. This is the cost for this alternative. This is the number of lives saved. So on and so forth. Okay. So now, then I draw a line. Then I drew a line that only connects alternatives A, B, and D. Why do you think I don't want to draw a line through alternative C? In fact, if I look at this chart, as a decision maker, I don't like alternative C. Can you think of why don't you like alternative C? Why might not you like alternative C? So you could see that because C is not as efficient, because it doesn't save as many lives per dollar spent, and it falls below that trade-off surface, I want to exclude it from further consideration. So there will be a homework problem based on this that you will see. Okay. Let's move on to the next thing. Valuation. Okay. Now, in some cases, you might have two non-dollar quantifiable. And then this is, again, maybe it's a pipeline or whatever we're doing in Alaska. So let's say you have $2 non-dollar quantifiable MOPs, measures of performance. One of them is acres of moose habitat lost. And then on the other side, you have increase in stream turbidity. And those are both sort of less desirable outcomes. But you can create a trade-off surface through that. And then here, you will exclude this alternative because you lose more moose habitat and you still have same amount of increase in stream turbidity. So you don't want that. So that's basically the idea, is that you want like more desirable characteristics, and if you're going to lose more moose habitat, you want to minimize the increase in stream turbidity. So if you are going to lose this much moose habitat, you want to be here. If you want to lose this much moose habitat, you want to be here on the. So you don't want to lose more. You don't want to lose more moose habitat for the same increase in the stream turbidity. You don't want that, and that's why you exclude the circled alternatives from consideration. And then your trade-off surface becomes the line that passes through the remaining ones. Any questions about this? Does it all make sense? Okay. Looks like it does, so we can move on. And then there is something called a factor profile. And factor profiles are useful when your number of alternatives is not as many, but you have many measures of performance. And one thing I'll say that these notes is something that I created a while ago. But one thing I always do that, and if you're going to take a safe transportation safety class with me next quarter, you'll see me do that all the time, is that I'm going to not call it accidents. I'm going to call it crashes. Okay. So I'm just going to call it crashes or collisions and not accidents. That's something that we learn in traffic safety. So we'll call them crashes. But more relevant to what we're talking about here is that factor profiles is another way of looking at alternatives and different things. And one of the things that comes into play there is that this is useful when you only have like few alternatives. So like, can you tell me by looking at this figure, how many alternatives are we evaluating? You can type that up in the chat. How many alternatives are we evaluating here? Let's see some messages in the chat. 3, that's right. A, B, and C are my alternatives, but I have cost, crashes, pollution, inaccessibility, and jobs lost. So 5 different measures of performance. And then I can draw where each of them is with regards to. So as an analyst, your job is to figure out where each of these alternatives fall as cost, crashes, pollution, inaccessibility, and job loss. So basically, this is your analysis of internal evaluation of alternatives, and you're quantifying all these different impacts for all these different alternatives. And then a decision maker would come in and say, hey, and then they can decide what's the most important thing for them. Maybe you want to minimize the job losses, right? And then just pick the alternative based on that, and that's okay, Or maybe the pollution is sort of important to you, so maybe you definitely want to pick the one that minimizes pollution. So there could be multiple things that you could look at that make you decide. And there could be, different weights assigned to these things. But again, in this chart, you can at least see what your trade-offs are between different alternatives. Okay, so this is what we call a factor profile. If you look at this is what's called a factor profile, and this is how you draw it. And this is useful when you have few alternatives, not as many alternatives, but a lot of measures of performance. And then you can also look at, similarly, using a goals achievement matrix. A goal achievement matrix is very similar to factor profile, but here we're not actually concerned about the nominal value of the pollution or job loss and whatnot, but instead I have a threshold on each of these criteria. I have a threshold on cost that I don't want to spend more than this money. I want to have fewer than that number of crashes. Again, I want to not use the term accidents, and I'll modify that. And then I want to minimize the pollution to this level. So for each of these things, you have a goal specified. And then I have this very subjective one, ugliness, and that basically might be just decision makers looking at, how does the alternative actually looks? Does it have any aesthetic implications and so forth? If it does, then you basically, if it for decision maker doesn't look nice, then you just think, okay, yeah, this doesn't meet the goal that we are trying to meet in terms of the aesthetics. So again, it could be a quantifiable threshold on cost, number of crashes, or pollution, particulate pollution, or whatever. Or it could be a subjective thing. Yes, no, this looks ugly, or this looks beautiful, or whatever, or this meets our aesthetics criteria, or this doesn't meet our criteria. But a goal achievement is very similar to factor profile, but instead of looking at actual numbers, you're just looking at thresholds, whether or not you meet that threshold. And then you can have sort of a dynamic goal achievement matrix that kind of looks at the time, right? So the cost in 5 years' time doesn't exceed this. Number of crashes reduced in 5-year time go to this. And the pollution from 1 year from now should be this. So you could have a sort of a third dimension of alternative, these cost, crashes, and pollution goal met or not, and then over time, in year 1, year 2, year 3. So you can have a dynamic goal achievement matrix. You can also have a social accounting framework. And a social accounting framework, it adds the dimension of the interest group that is affected by. Okay? So you could have, how does that impact particular community? What's the pollution that's going to occur in a certain community because of it? And are there different communities going to be impacted differently by different alternatives? So are there one community that is disproportionately impacted by one of those alternatives? Then that's something that you might want to look at. And that's what we call the social accounting framework. So this basically concludes the lecture on the introduction of the systems analysis approach. We learned a lot of different things. But one thing that you want to make sure is that this is your homework problem. And the idea is that you are trying to create a new light rail mass transportation system for a medium-sized city. So maybe not quite San Luis Obispo, but maybe Fresno would be a good example. Fresno, California, a city population of about 400,000 people, and we're trying to create a new light rail mass transportation system. Although I don't know if Fresno will ever go for it, but let's go with it for now. And then I want you to look at measures of performance that you'll use. I want you to make a separate sublist of performance measures that impact the owner, the local transit agency, the potential users, and the surrounding community, both users and non-users. And then stratify each sublist into factors that can be quantified, and then factors that you would consider non-quantifiable. And so this is your homework run problem. I've posted this assignment on Canvas as well, and it's due before the lecture on Tuesday. Okay, so this is posted on Canvas, due on Tuesday. So please take a look at it. It should be a very quick assignment. Don't spend too much time on it. But this is something that I want you to think about. And this does conclude our sort of the first lecture that we are starting off with. So any questions, if you have about this homework or anything like that, or anything about this lecture at all? Okay, so this is our sort of start of our lecture 2, which is financial mathematics and benefit cost analysis. Now, where I'm going to start this discussion, you all know that discussion from CE 321 and CE 322, Introduction to Transportation and Engineering. We do talk about a lot there. So a lot of formulas, converting expenditures and receipts occurring at different time period to a common point in time. That's the whole thing we're dealing with here. You know, how do we convert money that is spent and benefits that are garnered over different time periods into a common time frame? And that happens because what is the importance of doing that? So let me sort of ask you guys a question. Why do we need to do that? Why do we need to account for expenditures that happen in different times into a common time frame? Why do we need to do that? Resume recording. So yeah, so I got some, like, the funding timeline of a project. So yeah, we might have to, so Grant might ask us to kind of do all of that analysis based on a certain year of dollars, and that's reasonable. But then why do the grant funding agency might ask you to do that in the first place? Because we have to account for the idea that money can earn interest. So inflation doesn't really come into play here. We're not really concerned about inflation here. Because we think about inflation affecting all these different alternatives in a similar way. Inflation may have an impact on the interest rates regime that you're going to assume. So that's an indirect impact, but typically we are not necessarily worried about inflation. But because the money can earn interest sitting in a bank account or whatever, maybe it's very little interest if the interest rates are low enough. But whatever it is, it could have earned that interest, and now it's not doing that. So every future dollar is not as valuable as the dollar that's in your hand today. And that's why we need to make sure that we are comparing apples to apples and kind of bringing all the money into the same time frame. Okay, so not quite inflation related, although inflation might affect the interest rate, but it's about the ability of the money to earn interest that dictates all of this. Next slide. So this is the basic principle. Amount of money you receive or spend today has more value than a dollar that you get a year or 2 years from now, because money can be invested to earn income over time, right? So if you have an investment opportunity paying 12% real return annually, so if you have an investment opportunity doing that, you just tell me what that opportunity is, first of all. I'm all in on that. Okay? But because there are very few opportunities these days that get you 12% interest anywhere. But if you have that, and we always assume that the real return. So anytime you see in any of these problems where we're going to specify interest rate and all of those things, they're going to be real returns. They're not going to be they're going to be inflation adjusted return. So anytime you see an interest rate in any of the problems, just assume that it's already interest rate adjusted. So that's why we never actually have to account for inflation when we do this analysis. But let's say if there is an investment opportunities with a 12% return, $1 today is the same as $1.12 1 year from now. So basically what would happen is that to account for having that $1 in your hand today, you will say that, hey, if you're going to give me that $1 1 year from now, I'm not just going to take $1. I'm going to need $1.12 if you're going to give it to me in 1 year. If you're going to give me same thing in 2 years, it'll be 1.12 squared. So I'm going to need actually $1.25 2 years from now. If you're going to give me the money in 2 years, either you give me $1 today or give me $1.25 2 years from now. Okay, so that's how we account for it. $1 into the future has inherently less value than the $1 that's in your hand today. Okay? And again, this is just a rehash of the basic principle. Any doubts about that? Anything that you are concerned about on this? Anything that concerns you about this? You can either type up that question in chat, or you can ask me that question via voice. Okay. So that you guys know this, so that's good. And then there is compounding, right? And then that's what happens, like 12% interest that compounds monthly, 12% annual interest that compounds monthly. The $1 will be same as, so you basically divide the interest rate by 12. So let me go ahead and annotate this. So you can see that here. You can see that here as well. So if you have 12% annual interest rate, but it's being compounded monthly, then basically you have to figure out how many compounding periods are there going to be. So if it's compounded monthly, that means your interest accrues every month. But because the interest rate is annual 12%, it's basically 1% monthly interest rate. So every month you earn that 1% money on your sitting account, sitting money, and then you compound it over 12 compounding periods. So your $1 today would be the same as 1 plus 1.01 raised to power 12. That becomes 1.268. Okay. So what I'm going to do is I'm going to give you a problem, real quick problem to solve here. And let's see if you can do it. Pause the recording, resume recording. So my question to you is, if you have $1 today, what is the equal amount to $1 today, 2 years from now, and your interest rate is 6%, and it's compound, and 6% interest rate is annual, 6% annual interest rate, compounded quarterly. So I finally have this right, I think. Okay, so let's try to work that using a calculator maybe. And how, so let's say if it takes a couple of minutes, that's fine. What we're trying to figure out is, if you had $1 today in your hands, how much money would you want that will be equivalent to that $1 2 years from now, if you have 6% interest rate, annual interest rate, compounded every quarter? So it's basically using the example that you see on the slide. Let's try to get to it. I'll pause recording and give you 5 minutes to work on. So let's figure out, for the given problem, the different components of this equation right here. So we said the interest rate is 6% annual. So what is the equivalent interest rate for every quarter? Because we are compounding quarterly. So what's the equivalent interest rate for the quarter? You can type that up in the chat. Anybody? Yeah, 1.5%. That's right. It's going to be 1.5%. How did you get to that point? Because it's 6 divided by 4. Because there is going to be 4 compounding periods every year. So you're going to earn 1.5%. And then that 1.5% will add to your principal and start earning interest. Right? And that's why it's going to be 1.5%. So this number, so what you're going to end up here is 1 plus 0.015. You see that? $1.015, right? And how many compounding periods would there be if it's 2-year period? How many compounding periods would there be? How many compounding periods would there be? You can type it up in the chat. In 2 years, 8. That's right. So how you do it is basically you do raised to power 8. So that's what I did. 1.015 raised to power 8. And I did not get the numbers that you guys reported. So tell me, what do you get when you do this? You can type that up in the chat. Yeah, 1.1265 is what I got. If I go 4 decimal places, I got about 1.1265. And that's right. Any questions about this? Because you're going to be doing a lot of such calculations, lot of such calculations for the homework that I'm going to assign next Tuesday or coming Tuesday, and also for your, for your labs and stuff like that. So a lot of these calculations need to be done. Okay, all right, so that's good. And then obviously there is a concept of continuous compounding, and that's where you're not actually doing this raised to power stuff. You're basically taking an integral of that. So you're integrating instead of just doing, but discrete compounding is what we typically use. So in practice, we always do discrete compounding, like the one example that you see here. But there is a concept of continuous compounding that you could search up if you're curious. But for the most part, you're always dealing with discrete compounding, like, at different periods, the money starts to compound. Okay, any questions about this? I'm going to move on then. So this is the generic formula that you could have. You could convert the future value into a present value. So future value is equal to present value times 1 plus I raised to power n. And we call that single payment compound account amount factor. And then you could rearrange that equation to get the present value. You'll just do future value divided by 1 plus I raised to n. So that's single payment present value factor. Okay, so that's sort of what we call it. But you're basically converting future value into using the present value, or you can get the present value using the future value. Okay, so that's just a formula for that. And then obviously, the n is not like number of years, but it's number of compounding periods. So if the money compounds more frequently than annually, then you have to account for n. So n is not number of years like we learned in CE 321, but you have to think of n as number of compounding periods. And then I is the equivalent interest rate for that compounding period. Oops, I need to clear the annotation here. Now, this I has several identities. In financial analysis, I is represented as the interest rate. In economic analysis, we call it discount rate or rate of return. And in engineering economics analysis, I is the real rate of return over inflation. So anytime you see an interest rate in any of the problems that we do in this class, and then any engineering economics analysis really that you have to use an interest rate of I% or whatever, that is just real rate of return over inflation that you could have potentially earned had you not done the project. Had you not spent $1 million or $5 million or whatever your initial investment is, had you not made that investment, how much money you could have earned, that agency would have earned excuse me, on on that money is how we think about I. Okay? We'll come back to this another one more time a little bit later. Remember this cash flow diagram, very important concept. In cash flow diagram, we don't apply adjustments because we are pointing the money in different years. We are plotting the money in different years. So whatever is the nominal amount, we just put that. We don't have, when we are drawing the cash flow diagrams, we don't apply adjustments. We don't convert money into same amount because we are demonstrating that money. Remember, we are demonstrating that money in that year that money is spent. So you can see that amount A is being shown in year 1, year 2, year 3, year n minus 1, and whatnot. And because you're showing the money being spent or being earned in that year, that's why you don't tend to adjust anything. You just put whatever so if every year you get an equal payment of $500, you just put that $500 in the cash flow diagram. You just provide it that way. Because it's just more of a visual tool to illustrate the expenditures and receipt over time. And because you're showing the money on the time scale when the expenses happen, you don't actually adjust it. All the adjustment, obviously, in your calculation, you have to make those adjustments. However, you don't make adjustment when you're drawing the cash flow diagram. Remember this for the lab. Okay, when we do the lab, I will ask you to draw a cash flow diagram. And I know question comes up, should we adjust? Should we not adjust? No, you don't adjust when you do the cash flow diagrams. So cash flow diagrams will represent the nominal flows without accounting for present value or future value, because you show that money coming in or out or going out in the same year that it's being done. Okay. Now, if you had money coming in every year, and in 321, I don't talk about it. In 321, what I do is that I just give you this formula and I just give you this formula. Okay. But where does that formula actually come from? Is that if you want to figure out what is the future value, if you're going to get $500 every year, what is its future value? If you want to figure that out, basically what you want to do is you want to make adjustment right here. So first 0th year, you get an A amount, so no adjustment is necessary. And then A times A, 1 plus I, because it's the first year's amount. A times 1 plus I squared would be the second year's amount. And then what you do is, and then once you add them all up, you get that future value, because you're adjusting individual payments from every year for that future value adjustment. So you're doing that. And that's the formula we saw in the last slide. And you do that adjustment for this year, for this year, for this year, and all that. And then you take that equation, you multiply that equation by 1 plus I. Okay. Okay, so then you get this expression. If you take this equation and multiply both sides by 1 plus I, and then everything just goes up by the power of 1 plus I. So this A times 1 plus I, and this 1 plus I becomes 1 plus I squared. 1 plus I squared becomes 1 plus I cubed. 1 plus I raised to power 3 becomes 4. And then n minus 1 becomes n. Right? And then you subtract the two equations. And then once you subtract it, you can solve for what we call the future value as a function of the annual payment. Okay? And then because we know the present value is future value divided by 1 plus I over n, you can come up with this formula right here, which is converting an annual series of payments into their equivalent present value. Okay, and we call that the present value factor or uniform end of year payments. So if you have some uniform end of year payments that you receive, you can convert them all into present value. If you know the A, and you know the interest rate, and you know the number of years, then you can come up with a present value. And this is the formula that you must have seen in CE 321 and 322, or when you're preparing for your FE exam and whatnot. Okay. Does that formula, where it came from, does that make sense now? Any questions? I'm not going to ask you to derive this formula in the class or in any of these things, but it's good to be knowledgeable about that, where it comes from. And then obviously we're going to use extensively this formula in our classes. And this is something that you know from before too. So let's go back to the next slide here. What do you do if the payments are monthly or quarterly, not annual? What do you do? We talked about already what we do. We just have to figure out how many payment periods there are, right? So you just use that information and then work out that way. And then you obviously adjust your annual interest rate into a corresponding quarterly or monthly rate and whatnot. We know that. No problem. Just use equivalent monthly or quarterly I values, an appropriate number of corresponding periods. We just did that for a 6% annual interest rate with a quarterly compounding. What to do if your cash flow is not uniform? If you can see a pattern, maybe you can do a pattern. But an easier way is to just use Excel. In that case, just use some computer program and just have okay, wherever those payments occur, convert those individually using computer program into present value and just add up the present value. So in worst case, discount, and this worst case method, that would work for you every time. Because it's a general method. Discount individual payments to present and sum the results. If there are some constant increment gradient series, there are formulas for that. And then Excel has some more formulas that you could use as well. But you don't have to always get into that. You could just discount individual payment to present and just go with that. Questions? Okay, not seeing any questions, so I'm going to move on. So in the life cycle cost analysis, the best practice is to consider the full cash flow of costs and benefits over a long period of time on the order of the life cycle of the project. The life cycle captures costs and benefit effects of initial investment, maintenance and operation, during early operation, as well as the age sets in and replacement becomes relevant. And sometimes there is some salvage value. When your project is of no longer use, maybe you had some metal and whatnot, so you can salvage for something. And sometimes it's the other way around. Sometimes there is closeout cost because you have to clear out the site because now your project is finished. After 20 years of service life, it's over, but you have to clean out the site and make way for the next thing, right? So you have to account for those costs sometimes. Okay? So, but the idea is that we have to account comprehensively all the costs, all the benefits, and as the age sets in, maybe more costs and more benefits and less benefits, whatever. So we have to account for everything. So here is the thing. There is not just one criteria that we use. You can define costs and benefits, C and B, as the values of streams of costs and benefits respectively, discounted to a common year, and usually the present value. So it's usually going to be present value at rate I throughout the number of time periods, N. Net present worth is basically you take the present value of benefit and you subtract the present value of cost, B minus C. Sometimes you might have to convert that into annual value. We'll come back to that when we have to do that, although we do talk about it in 321 as well, but I'll remind you. So I'll remind you, when might we have to, does anybody recall that? When we might have to convert net present worth into its equivalent annual value. Does anybody remember that? When might we have to convert the net present worth into an annual value payment? So I heard one of the responses on the chat. Yes, when comparing alternatives of different lengths of time. So when you have one project that's going to last 5 years versus one project that's going to last 10 years, you cannot convert everything to present value. In fact, in that case, if the one project and two projects that you're comparing, or two alternatives that you're comparing, have different lifespans, then you want to convert everything to annual amounts. So you get the net present worth first for each project, and then you use the annual value factor to come up with annual value for both alternatives, and then just use that for comparison's sake. Okay, so that's exactly right. Thank you, Brian, for pointing out that we look at these things when we're comparing alternatives of different lengths of time. You can use simple benefit cost ratio. And these net present value and simple benefit cost ratio is something that you know from CE 321. So I only provide that here for the sake of completeness. We're going to learn about incremental B by C ratio. We're going to learn about internal rate of return, IRR. And what is the internal rate of return? It's called I value, where costs are equal to benefits. What is the interest rate at which cost becomes equal to benefits? And then there is the concept of incremental IRR. We'll discuss that later. And then the payback period. So the last four that I list here, payback period is the period, number of years or periods needed where benefit exceed the cost. Right? So last four that I'm assuming that you haven't seen before. So these will be the new items that we are going to be covering. And you're going to be estimating that for your lab as well. Okay. So we'll learn how to do that in this lecture. So let's clear this out. Now, one thing that we don't talk about enough in CE 321 is that to net present worth and benefit cost ratio, do they always give you similar answers? Do they always work in a similar way? So I'm giving you here two alternatives, A and B. And again, this difference is very, very exaggerated. It's like, the total cost is $2 million, and then total benefits is $2,002,000. And there is another alternative, which is only a $2,000 alternative. And then total benefits is basically $3,000. And I'm assuming that these are all converted into present value. So total cost in present value. So when I say DISC, what I mean by that here, so DISC stands for discounted. When I say discounted, means it's already converted into present value. Right? So if you take the net present worth value, A has a net present worth of 2,000 and B has a net present worth of 1,000. And that's because it's just a difference between benefit minus the cost. Because we know net present worth is B minus C. That's it, right? But if you do B divided by C, you get a different picture. It's alternative A has only benefit cost ratio of 1.001, alternative B has 1.5. So it's not so much I'm giving you this discussion as to which one would you choose. Personally, I'll just go with B because I'm cheap. So I'll just kind of start with cheapest alternative and go with that. But that's not the discussion I want to have here. The discussion I want to have here is that, and the differences will never be this exaggerated between the two alternatives. But this still provides a good contrast as to what are the inherent biases that exist with metrics such as net present worth and metrics such as benefit cost ratio. You can see here, because of this exaggerated example, that the benefit cost ratio has a bias towards small projects, right? Where the costs are minimum. That's what it's biased towards. But net present worth is typically biased towards, because it's just a simple difference. That one is biased towards very large capital projects. And you could see that because it's a difference. And obviously, if you spend more money, you can probably get more benefits. And just the algebraic difference between the two would be larger. Numerical difference between the two would be larger. So you could see that the net present worth has a bias. So if you use net present worth as your metric for evaluation, you're going to create a bias towards larger projects. But if you use benefit cost ratio, you will create a bias towards small projects. Now, what to do? So you have to think about context. First thing that you will so how do we account for that bias? And now this is where the discussion starts to move on to a higher level than you might have picked up in 321. How do we decide that? Any thoughts on how do we decide what to do now that we know about the biases of the individual measures like net present worth and benefit cost ratio? Any thoughts on that? I'm not hearing any responses or getting any responses in chat. So I'm just gonna sort of give you a very unsatisfying answer. It depends. What we do, it just depends. What it depends on is your judgment. You obviously, what you'll do is you'll look at other measures. You'll be aware of every measure's bias. And then you'll recommend alternative, which makes the most sense. And that will come with practice. You cannot come with like, okay, what makes most sense? It's a very hard question to answer, especially when you're starting out with this stuff. But what we'll do is when we do a lab project that we're going to start on Wednesday, you will learn more about what to do because you're going to have to do it for one of the one of the evaluation analysis. Okay. So we'll learn about what to, and then obviously we're going to look at other measures first. We look at other measures, and then if they give us a clear answer, then we go with that. But if there are still sort of conflicts, then we exercise judgment. And again, this is a very, very exaggerated example. So you're not going to get this level of sort of this absurd level of difference between the two alternatives. But you'll still see some contradictions as you look at multiple measures. And you're going to learn to exercise that judgment. So let's see. Okay, I'm going to stop here because I won't be able to finish this discussion. So I'm going to stop here and we'll talk about the internal rate of return in the next class. Okay. If there are any questions, you can hang out here. If there are no questions, I'll see you guys in the next class.